Okay. Please welcome Daniele De Sensi from ETH Zürich, who will be presenting his work on congestion mitigation in large distributed system for high-performance computing.
Hello, I am Daniele from ETH Zürich, and today I will present my research work about optimization techniques for high-performance interconnection networks. So my research lies in the fields of large-scale distributed systems, computing systems, and you can see one of those in this picture here. So these are systems that are basically large computers made of many different computers or servers. In this figure here, you can imagine each of these green lights being one of these computers or servers. And you have hundreds of thousands of them in one single room, and these computers are connected between each other to solve some scientific problems. And they're used for many different reasons. For example, they are extensively used to perform weather and climate modeling simulations, for example, to predict where and when a hurricane is going to strike. But recently, they've also been used, for example, to help researchers find a vaccine for COVID-19. And actually, you also use them in an indirect way in your everyday life. So every time that, for example, you type a search on your web browser, your research goes through one of these systems that will look up into billions of web pages trying to find what you're looking for. So these are key computing systems that we use in one way or another in our everyday life. And to understand how these systems work, let's consider, for example, this use case where they're used for performing weather and climate modeling simulations. So in this kind of applications, you have basically a map of the world of one region of the world, and this map is split in multiple parts, and then you have one server working on each of these parts. So each of the servers try to simulate what's going on that area of the world. But what you might have is that in some cases, this server needs to communicate to progress with the simulation. So this server here on the top right, for example, might have some data to exchange with this other server to understand how the hurricane is moving from one side to another. And to perform this kind of data exchange to progress the computation, these servers need to be connected together with what is called an interconnection network. So that in this case is denoted in green. This interconnection network is made by links that are these green lines, and by these other devices that are called switches that basically move data from one side to another. And what I do in my research is to optimize this interconnection network and try to make it as fast as possible so that data is exchanged at a faster rate. I'll try to be very generic in this presentation, but if you have any question, please, you can ask me later. So let's focus just on these four servers here, and let's suppose that they need to exchange some data between each other. So data is basically wrapped inside what is called packet. A packet is basically a chunk of information that needs to be transmitted, and we denote this packet with these orange boxes here. So now what happens is that, okay, let's suppose that this server must send some data to this server. They select a path on the network, so a set of links that connect the source to the destination, and they start sending the data on these links. And then let's suppose that this one on the top right needs to send something else to the one on the bottom left. They also start sending the data. But as you can see here, now the data moves slower because both of these connections goes through the same link in the network. So because this is a physical resource and it is shared by these two connections, data moves at a slower rate. And so this is one of the problems that you might have in this kind of systems. So what is typically done? So we call this situation here as a situation of congestion because you have multiple pieces of data going through the same physical devices. What it is usually done in this case is that someone starts sending the data, and then before this server here sends its own data, it observes what is going on the network, and it observes that there is congestion on this link, and it decides to take a different path. So that in this way, the two connections goes onto these joint paths, and both of them can transfer data at full speed without interfering with each other. But doing so introduces some complications. So, for example, what often happens is that this one starts sending the data, this one realizes that there is congestion and decides to take a different path, but in the meanwhile, this congestion disappears. So now we have this data moving on a longer path, even if there is no congestion anymore on the shorter one. And this might be, we actually studied this and we realized that this is a very recurrent problem and a very relevant problem in many existing applications and many existing networks. So what we have done is basically to find ways to have the right trade-off between how sensitive we are to the congestion we observe, so that we avoid such kind of situations. And we applied these techniques on many different applications, reaching up a performance improvement up to 2x. And we validated this approach on real systems. So at that time, it was the most powerful supercomputer in Europe, and over many different real applications, including weather and climate modeling, molecular dynamics simulations, computational fluid dynamics, and many more. Another related problem is about data aggregation. So we have many cases where you have two servers and you want to aggregate two or more servers, and you want to aggregate together the data coming from these servers. So the data reaches the same server. The server does some computation on this data and creates some new piece of data that then need to be distributed to both of them. And what we can do to improve the performance of this operation. So this is a very common operation, for example, in machine learning, when you train a model to, for example, to translate languages or to identify objects in pictures and so on and so forth. So this is a very common operation. What we can do instead is to let these network devices do some computation. So instead of sending the data from one server to another, both servers send the data to the same network switch. And this intermediate device here does the computation, obtains the new results, and distributes the results to both servers. And it has been shown that this can improve the performance of such kind of operations. But the question here is how this device is made. So what's actually inside this network switch? So these are devices that, as I was mentioning at the beginning, are designed to move data around. And if we have to make some computation there, then we need to design some new hardware. And this is exactly what we did. And we validated this hardware on some real use cases, showing up to a 2x reduction in the time spent for this application in the communication. And we validated this on an application, on a machine learning application, identifying objects in pictures. So identifying whether there is a cat in a picture, a car, or something else. And of course, we are moving forward with this research. There are other research directions we are exploring. So for example, if you consider the two examples I just made, so in one case, we say that we want to send the data where there is less congestion. So we want to have a lot of freedom in where we send our data to avoid congested area of the network. But in the other case, we need to we say that we want to process the data in specific points of the network where we want to aggregate this data. And these two requirements are conflicting between each other, because if you want to aggregate these two pieces of data together, we might want to aggregate them here, or here, but we have to decide this before. And this goes against what we would like to do when we want to avoid congestion, because in that case, we want to send the data wherever the network is less congested. And so we are working in such a way that we can somewhat combine and find better techniques to satisfy both requirements. Another problem we are analyzing is about data reordering. So in this example, this server sends first the orange packet and then the blue one. But what happens is that if they take different paths on the network, they might arrive at the destination in a different order. So in this case, the destination receives first the blue one and then the orange one, but this is a problem for many different applications. So there are applications where packets might arrive at the destination in the same order they were transmitted. And this, again, goes in conflict with the requirement that we want to send the data wherever we want. And we are working to address these issues. And the last one is about network security. So in many cases, data is encrypted. So actually, I would say most cases data is encrypted. So in these cases, if the switch in the network must process this data, then this is a problem because the switch might not have the decryption key to unlock this data and then process the data content. So this is also something we are working in. We are working on right now. So this was a very general overview of my research. If you have any question, please, you are welcome to ask. I would like to acknowledge Professor Thorsten Offe, that have been my supervisor at ETH Zurich, and all the people I've been lucky to work with in our lab. Thank you.
Thank you so much, Daniela, for that insightful talk. And we are here for the question answer session. I'm just quickly going to check on the live session if there are any questions yet. But if not, I would start off with one question. I was wondering, like, you've taken inspiration from the road networks to mitigate congestion in like supercomputing resources. So I was just wondering if you could give a bit more insights on like how was the computation cost and like how much computing time did it take to come up with an optimal solution, because these are like quite complex systems that we are looking at here.
Yeah. So of course, like in this case, we can't hope to have some kind of centralized solution. So as it happens, for example, in road networks. So like, for example, if you use some kind of navigator, typically you would have the status of all the roads on the network, and it will try to find an optimal path. But in this case, since we are working on a much smaller time scale, so here we are talking about nanoseconds or microseconds, such solutions will not be very feasible. So each switch or also the endpoint must take decision only based on the local information that they have. And this means that the time required to process this data is much smaller because you only have the data about the host or the switch is directly attached to you. And at the same time, this means that the accuracy is lower. So we are just taking decisions based on local information. So this is faster to do, but it's also more, it's not that accurate as a decision taken on with a global view of the network. So of course, these are heuristics, and we are happy if we can somewhat match more or less closely the ideal performance, but we at the moment we are not able to get that close.
Right. Yeah, that's great. I mean, near optimality also in such cases is quite useful. So that's really nice to have. There's a question on chat which says, I have not understood what tools you use to solve these problems. Is it rather mathematical, logics, or something else?
Yeah, so this, again, so even in this case, we could use some kind of complex graph theory approach to solve the problem in an optimal way. But again, we don't have the information about all the links in the network. So eventually these are heuristics. So in some sense, basically what each of these switches see is just the occupancy of the queues of that switch. And based on that, basically, you have to apply some heuristic to, for example, to check if the gradients of the queue size is increasing or not. So to understand whether things are getting worse, and then if you have to route the packet somewhere else. So there is no, let's say, strong theoretical graph algorithms behind that, just because we don't have the view of the entire graph, but just of a small part of the network. So these are mostly heuristics. So yeah.
All right, there's one more question we have time for. Says really interesting talk, and the examples where a switch is doing some computational analysis, would it not be more efficient to have instead a dedicated node that does the computation?
That's a very good question. So the main issue here is that if you have a node, so for example, if you buy a server somewhere, or just usually you will have one network port. Like these switches have like 64 or 128 network ports. So just the rate that they can inject and process, it's much higher. So this is the main reason why. And the other reason is that if you do this with an actual node, you will need to move the computation from the network to the CPU, and then to get and the data from the RAM and back and forth. And this will introduce a latency which is too high. Well, these switches have some kind of dedicated architecture that are designed for have all this data movement done in a much efficient way. So this is the reason why having an actual node inside the network would be much less performing than doing this on a switch.
Right, great. We might have one more time for one more quick question. Perhaps, like, I was wondering, like, is there any contextual information that you could use to improvise on your heuristics that are being applied? Like, is there any application-specific context that might help you get better heuristics in this case?
Yeah, so there are some info, and actually we are exploiting that. So there are some information that the application can provide. So, for example, how large is the size of the data that you have to transfer? Because in this way, like if you know that you have to transfer a very large message, for example, you can pay a little bit more overhead to find an optimal path at the beginning, and then like being more safe during the transfer. While if you have to transfer, for example, small data messages, then it's probably just worth to send the data wherever you want, because otherwise that overhead will be much higher than the gain that you will get by finding a better solution. So yes, this is one type of information that the application can provide to drive better decisions in the network.
Awesome, great. Thanks so much for your time, Daniela. We'll go
Thank you
on
for
to the
having me
next.
here.
Thank you. We'll go to
Thank
the
you.
next speaker now. Take care.